What does it take for a promise to die? Not a promise between people whispered in quiet rooms, but a promise on a cosmic scale, one written in ice and dust across the vast, silent canvas of the solar system. For all of human history, they have been our most unnerving messengers, our most profound omens, celestial phantoms appearing without warning in the placid night, their luminous tails stretching like ghostly fingers across the familiar constellations. The ancients saw them and trembled, interpreting their arrival as a harbinger of war, the death of kings, or the wrath of gods. A fiery sword hanging in the heavens, a celestial portent that shattered the comforting illusion of an orderly, unchanging universe. They were cosmic intruders, wild and unpredictable, their paths seemingly governed by a logic entirely alien to the steady march of the sun and the gentle waltz of the planets. We now call them comets. We understand them not as divine warnings, but as something far more wondrous, pristine relics from the dawn of creation itself. They are time capsules born in the frigid, dark nursery of the outer solar system, the Oort cloud, a theoretical sphere of trillions of icy bodies encasing us at an almost unimaginable distance. For millennia, they have slept in that deep freeze, silent witnesses to the birth of stars and the death of galaxies. But occasionally, a subtle gravitational nudge from a passing star, a slight jostle in the cosmic fabric is all it takes. One of these sleeping giants is dislodged from its tranquil orbit and begins a long, slow fall, a journey of millions of years toward the distant beckoning light of our sun. As it crosses the threshold into the inner solar system, the sun's warmth begins to work its magic. The ancient ice, frozen for longer than humanity has existed, starts to sublimate, transforming directly from a solid into a gas. This escaping vapor erupts from the nucleus, carrying with it dust and rock trapped within, creating a vast glowing atmosphere called a coma, which can swell to be larger than the planet Jupiter. The relentless pressure of sunlight and the solar wind then pushes this material away, sculpting it into the iconic ethereal tales that have so captivated and terrified us throughout our existence. We have learned to anticipate their arrival, to plot their courses, and to see them not as omens of doom, but as opportunities for discovery. They are couriers from a forgotten time, carrying the raw primordial ingredients from which Earth, and perhaps even life itself, was formed. And among these celestial visitors, a hallowed few achieve a legendary status. They are the ones that defy expectations, that blaze so brightly they become visible to the naked eye even in daylight, their tails spanning immense swathes of the night sky. We call them the Great Comets. They are celestial royalty, their appearances marking generations. The Great Comet of 1811, which hung in the sky for months, was so spectacular it was woven into the pages of Tolstoy's War and Peace. In the 20th century, Comet Hale-Bopp in 1997 became a cultural touchstone, a shared global experience that prompted millions to gaze upward in collective wonder, a serene and majestic presence that lingered in our twilight skies. The arrival of a new great comet is more than just an astronomical event. It is a promise. A promise of a spectacle that can unite us, that can momentarily lift our gaze from our terrestrial concerns and remind us of the sublime, awe-inspiring grandeur of the cosmos we inhabit. It is a promise that science prepares for, that the public eagerly awaits. In late 2019, it seemed that such a promise was once again being made. The discovery was not made by a lone astronomer peering through a brass telescope on a remote mountaintop, but by the tireless robotic eyes of a modern celestial sentinel. The Asteroid Terrestrial Impact Last Alert System, or ATLAS, is a pair of fully autonomous telescopes in Hawaii programmed to scan the entire visible sky every few nights. Their primary mission is a somber one: to detect near-Earth asteroids that might pose a threat to our planet. They are our planetary defense watchdogs, sifting through an endless river of data for anything that moves, anything that changes. On the 28th of December 2019, the system flagged a new faint smudge of light in the constellation of Ursa Major. It was designated C 2019Y4, a typically dry clinical name for what would soon become a global sensation. At first, it was just another data point among thousands, a minor blip on the cosmic radar. But as astronomers around the world began to track its trajectory, a thrilling narrative began to unfold. This was no ordinary comet. Its orbit was the first clue. It was a long-period comet, its path so stretched and open that it was essentially a parabolic arc. This told astronomers that it was a pristine visitor, likely making its very first journey into the inner solar system from the unfathomable depths of the Oort cloud. It was not a weary traveller like Halley's comet, worn down by repeated passages near the Sun. This was a fresh specimen, a virgin snowball carrying an unspoiled chemical record of the solar system's birth some 4.5 billion years ago. The scientific potential was immense, but it was the second clue that truly ignited the astronomical community and set the stage for public fascination. It was brightening, not just brightening, but brightening at a truly astonishing rate. Comets are notoriously unpredictable, their behaviour often likened to that of a cat, fickle and prone to sudden changes. But this one, now informally named Comet Atlas after its discoverers, was following the perfect script for a celestial blockbuster. Its brightness was increasing exponentially, far faster than most comets do as they approach the Sun. Early calculations extrapolated forward painted an extraordinary picture. By the time it reached its perihelion, its closest approach to the Sun, in late May of 2020, Comet Atlas wasn't just predicted to be visible to the naked eye, it was projected to become dazzlingly bright. The predictions were intoxicating, bordering on the unbelievable. Some models suggested it could reach a magnitude of 0 or even negative numbers, placing it on par with the brightest stars in the sky, perhaps even rivaling the planet Venus. There were whispers it might even become visible during the daytime, a ghostly apparition hanging in the blue expanse of our atmosphere. For a world heading into the unprecedented uncertainty and isolation of a global pandemic, the timing felt like a cosmic gift. Here was a universal spectacle, a celestial event that everyone on Earth could look forward to, a beautiful and profound distraction that promised to connect us all through a shared act of looking up. The hype machine, fueled by both scientific optimism and public yearning, roared to life. News articles proclaimed the coming of a once-in-a-generation comet. Astronomy forums buzzed with frenetic energy. Amateur astronomers, seasoned veterans, and newcomers alike began preparing their equipment, meticulously planning their viewing sessions for the spring nights ahead. Telescope sales surged. The public, starved for a glimmer of hope and wonder, latched onto the story of this celestial wanderer. Comet Atlas was no longer just C 2019Y4. It was a character in a global drama, the protagonist of a story we all desperately wanted to see reach its brilliant climax. Throughout February and into March of 2020, the comet seemed determined to live up to its billing. It continued its dramatic surge in brightness, its coma expanding into a beautiful greenish globe, its faint tail beginning to stretch out behind it. Each new image captured by astrophotographers was more stunning than the last, showing a vibrant, active comet behaving exactly as a future great comet should. It was performing flawlessly, hitting every mark its journey from the dark abyss toward the solar system's heart, looking like a triumphant march. We were watching a celestial coronation in slow motion, and the entire world had a front row seat. The promise was not just holding, it was shining brighter every single night. And then something went wrong. The first signs were subtle, easily dismissed as observational noise or the comet's inherent unpredictability. Around the middle of March, the meteoric rise in its brightness began to slow. The exponential curve that had fueled so much excitement started to flatten out. At first, astronomers urged patience. Comets, after all, have their moods. Perhaps it was entering a less volatile region of its nucleus, or maybe a crust of dust was temporarily insulating the ice beneath. But the plateau didn't end. By the end of the month, the situation had become alarming. The comet wasn't just failing to get brighter, it had stalled completely, and then inexplicably, it began to fade. The decline was gentle at first, a whispered retreat rather than a panicked flight. But it was undeniable. The celestial protagonist was faltering, the script was being torn up before our very eyes. The vibrant, condensed core seen in earlier images started to look different. It was becoming elongated, fuzzy, less defined. The sharp, stellar point of light at its heart was softening, as if it was losing its structural integrity. The buzz in the astronomical community shifted from one of joyous anticipation to one of worried confusion. What was happening to our comet? Was it simply an outburst of activity that had now subsided, a temporary flare-up that had given us false hope? Or were we witnessing something more profound, something more catastrophic? The debate raged. Online and in scientific circulars, theories were floated. Perhaps the comet's nucleus, a loose agglomeration of ice and rock, was beginning to break apart under the increasing thermal and gravitational stress of its approach to the Sun. This initial fragmentation could release a burst of dust and gas, causing the initial rapid brightening. But this would be a death cry, not a sign of vitality. If the core was disintegrating, the comet would not survive its fiery passage around the Sun. It would simply crumble into a cloud of insignificant debris. The dream of a great comet, the promise of a generational spectacle, was beginning to dissolve along with the comet's nucleus. For the millions who had pinned their hopes on this celestial visitor, the news was a slow-motion disappointment. The celestial coronation was turning into a funeral, and this is where our story truly begins. Because what happened next transformed this disappointment into a deep and compelling mystery. As April progressed, the fading accelerated. The comet that was supposed to be brightening into a spectacular naked-eye object was now rapidly dimming, falling back into the realm of telescopic viewing. And for the vast majority of people who had been tracking its journey, the backyard astronomers, the amateur enthusiasts, the families who had bought their first telescope, it entered a strange and frustrating void. It plunged into what we call the Blackout Zone. This isn't a physical place in space. It is a zone of observation, an abyss of visibility. It's the cruel gap that exists between the capabilities of professional mountaintop observatories or space-based telescopes and the equipment available to the public. As Comet Atlas continued to disintegrate, its light became too faint and, more importantly, too diffuse. It was no longer a concentrated point of brightness, but a ghostly spreading smear. For the millions of smaller telescopes on Earth aimed at the precise coordinates where the comet should be, there was nothing. Just the familiar, empty blackness of space. The promise had not only been broken, it had vanished. It had slipped through our collective fingers, disappearing from the very instruments that had made its discovery a public phenomenon. The show was cancelled, the stage left empty. While giant telescopes like the Hubble Space Telescope could be aimed at the location and could see the grim evidence of the comet's demise, a train of faint rocky fragments, a ghost of its former self for the public atlas, was gone. It had entered a realm of invisibility, its final catastrophic moments hidden from our view. This vanishing act poses the central haunting question of our investigation. What truly happened in the dark? What fatal flaw hidden within that pristine block of ancient ice led to such a spectacular and complete self-destruction? Was its demise a violent, explosive event, or a slow, quiet crumbling into dust by turning our most powerful instruments toward the scene of the crime? We sought to perform a cosmic autopsy, to understand the forces that turned a celestial marvel into an invisible enigma. The disappearance of Comet Atlas is more than a story of a failed spectacle. It is a profound lesson, a stark reminder that the universe is filled with objects of exquisite fragility. And by studying its death, by peering into that blackout zone, we can learn more about the fundamental nature of these cosmic travelers and perhaps uncover deeper truths about the violent, chaotic, and beautiful origins of our own solar system. The ghost of Comet Atlas has a story to tell, and we are now ready to listen. What if the oldest story in existence wasn't written in stone or whispered in myth, but was instead etched in ice and dust, waiting in the cold silence of space for its moment to be told? Imagine a messenger from a time before the Earth itself had cooled, a silent witness to the birth of our sun and the chaotic ballet of planet formation. For millennia, we saw them not as messengers but as omens. Flaming swords in the heavens, spectral apparitions that haunted the nightmares of kings and commoners alike. They were the harbingers of plague, the precursors to war, the very fingerprint of divine wrath smeared across the celestial sphere. Every culture, every civilization has looked up and woven its deepest anxieties into their ethereal, unpredictable glow. They defied the clockwork precision of the stars and the steady march of the planets, appearing as if from nowhere, blazing with an otherworldly brilliance, only to vanish back into the void from which they came. These celestial ghosts were a profound and terrifying mystery, a reminder that the universe was not entirely ours to command or comprehend. We filled the void of our understanding with fear, with superstition, with gods and monsters. But what we were truly seeing was not an ending but a beginning. We were looking at a physical remnant of our own origin story, a frozen breath from the solar system's primordial nebula. Today, the fear has largely subsided, replaced by a deep and insatiable curiosity. We now understand that these visitors are comets, cosmic icebergs composed of frozen water, methane, ammonia, and carbon dioxide, all intermixed with rock and dust. They are not divine omens, but something far more profound: time capsules. Locked within their frozen hearts is the raw chemistry of the ancient cloud of gas and dust that collapsed to form our sun and everything that orbits it some 4.5 billion years ago. They are pristine artifacts, unaltered by the geological turmoil, volcanic eruptions, and immense pressures that have reshaped every planet and moon in the inner solar system. To study a comet is to perform an archaeology of creation itself, and the story they tell begins not with fire but with ice and a journey of almost unimaginable scale. For most of its existence, a comet is inert, a dark, silent nucleus tumbling through the blackness. It's a mountain of ice and rock, often just a few kilometers across a misshapen, porous relic, so dark it reflects less light than a lump of coal. In the profound cold of deep space, hundreds of times farther from the sun than we are, it is a ghost among ghosts, utterly invisible. But its destiny is not to remain in the dark. A subtle gravitational nudge, perhaps from a passing star, or the tidal pull of the galaxy itself, can be enough to disturb its eons-long slumber. Over millions of years, this gentle push alters its path, nudging it from its stable, distant orbit and sending it on a long, slow fall toward the heart of the solar system. For centuries, for millennia, it travels inward, accelerating silently. Then, as it crosses the orbit of Jupiter, something magical begins to happen. The sun, once a distant, indifferent star, starts to become a powerful engine of transformation. Its warmth, even out here, is enough to begin stirring the ancient volatiles frozen within the nucleus. The ice doesn't melt. In the vacuum of space, it sublimates, turning directly from a solid into a gas. This outgassing, this celestial exhalation begins to shroud the dark nucleus in a vast glowing cloud of gas and dust. This shroud is the coma, and it can swell to become larger than a planet, a temporary atmosphere that can dwarf even the sun itself in sheer volume. Though it is infinitesimally thin, the silent dark rock has awoken. It has begun to sing its song of light, and this is only the beginning of its magnificent metamorphosis. As the comet plunges deeper, accelerating toward the sun, it encounters a force more powerful than heat alone, the solar wind. A relentless supersonic stream of charged particles flows constantly from our star, a celestial gale sweeping through the solar system. This wind slams into the fragile coma, stripping away ions and sculpting them into a long, straight, ghostly blue tail. This is the ion tail, a streamer of glowing gas pushed directly away from the sun by its magnetic field, a cosmic windsock pointing the direction of the solar gale. At the same time, the pressure of sunlight itself, the gentle but persistent push of countless photons, acts on the larger, heavier dust particles that have been liberated from the nucleus. This radiation pressure slowly shoves the dust into a second separate tail. This is the dust tail, a broader, more curved feature that shines a brilliant yellowish white as it reflects the light of the Sunday. It gently traces the comet's orbital path, a shimmering golden trail of breadcrumbs marking its journey through the heavens. A single dark frozen mountain has transformed into a radiant spectacle brandishing two distinct tails across millions of kilometers of space. The comet has finally become the celestial marvel that has captivated and terrified us for all of human history. Its brightness, its visibility, its very soul is a direct consequence of this violent, beautiful interaction, a celestial blowtorch igniting a mountain of primordial ice. But where do these incredible objects come from? Where is the nursery that holds these frozen relics of creation? To find their home, we must travel to the farthest, coldest, and most mysterious frontier of our solar system, a place we have never seen directly, but whose existence we can infer from the cosmic messengers it sends us. we must journey to the Oort cloud. It is not a cloud in any terrestrial sense, but a vast spherical shell of icy bodies, a cosmic minefield surrounding our solar system. Its inner edge is thought to lie thousands of times farther from the Sun than the Earth, and it may extend almost a light year into the darkness, a quarter of the way to our nearest stellar neighbour Proxima Centauri. This is a realm of unimaginable scale and profound emptiness. The objects within it, numbering perhaps in the trillions, are separated by millions of kilometres of perfect vacuum. Here the Sun is just the brightest star in the sky, its gravitational grip tenuous, almost an afterthought. The temperature hovers just a few degrees above absolute zero, a cold so deep it preserves these icy bodies in a state of suspended animation. They are the leftovers of planetary formation, the cosmic debris flung outward by the gravitational chaos of the giant planets in the solar system's youth. For billions of years they have drifted in this celestial deep freeze, silent guardians of the solar system's outermost border, a vast dark halo of pristine material. From this immense reservoir, a steady trickle of comets is sent inward, beginning the long pilgrimage that will eventually bring them into our skies. Those that complete this journey, that survive the gravitational bullying of Jupiter and the searing heat of the Sun, are known as long-period comets. Their orbits are so vast that they may take thousands, even millions of years to circle the Sun just once. When one of these appears in our skies, we are seeing something that has not visited the inner solar system since before human civilization began, or perhaps ever before. It is a truly fresh sample from the deep freeze, its surface unscarred by previous encounters with the Sun's intense radiation. Scientists prize these first-time visitors above all others, for they offer the purest window into the chemistry of our origins. To find one, to track it, to witness its first fiery awakening, is to open a book that has been sealed for 4.5 billion years. And in the 21st century, we no longer wait for these messengers to appear by chance. We have built Sentinel's tireless robotic eyes that scan the heavens night after night, standing guard over our small corner of the galaxy. They are not looking for omens or portents of doom, but for the faint, subtle movements that betray the presence of objects both familiar and new journeying through our cosmic neighborhood. One of the most prolific of these sentinels is the Asteroid Terrestrial Impact Last Alert System, or ATLAS. It is not a single giant telescope, but a pair of smaller, fully autonomous observatories, one on Haleakala and the other on Mauna Loa in Hawaii. Their primary mission is a sobering one: to scan the entire observable sky every few nights, searching for near-Earth asteroids, space rocks on a potential collision course with our planet. They are our early warning system, designed to give us years or even decades of notice before a potential impact. To accomplish this, the ATLAS telescopes take a series of pictures of the same patch of sky over the course of a night. Sophisticated software then meticulously analyzes these images, looking for anything that moves against the static backdrop of distant stars. Most of the time, the things that move are known asteroids, their paths well documented and understood. But every so often, the software flags a point of light that is new, an object not found in any catalogue, an unknown traveller entering our skies for the first time. On the night of December 28, 2019, the system did exactly that. It flagged a faint, fuzzy smudge of light in the constellation Ursa Major. It was moving, but it wasn't the sharp, distinct point of a typical asteroid. It was diffuse, hazy, a telltale sign of a cometary coma. An alert was automatically sent to the Minor Planet Center, the global clearinghouse for all such observations. Astronomers around the world turned their own instruments toward the coordinates. Follow-up observations quickly confirmed the discovery. This was indeed a new comet. It was given the official designation C, 2019Y, for Atlas, a technical name, signifying the year and half-month of its discovery and crediting the survey that found it. At first, there was little to distinguish it from the handful of other faint comets discovered each year. It was incredibly dim, a mere magnitude 19/2 50000 times fainter than the faintest star visible to the naked eye. It was located far out beyond the orbit of Mars, a distant speck on a long journey. But then astronomers began to calculate its trajectory. The preliminary orbital data told a stunning story. This was not a short-period comet trapped in a repeating loop around the Sunday. The calculations revealed a vast, nearly parabolic orbit, the hallmark of a visitor from the deepest reaches of space. Comet Atlas was a traveler from the Oort cloud, and it wasn't just passing through the outer solar system. It was on a direct course for a close flyby of the Sun, a trajectory that would carry it inside the orbit of Mercury. For a comet, such a path is a trial by fire, a perilous passage that can trigger a spectacular outburst of activity as its ancient ices are subjected to the full, unmitigated fury of the Sunday. Almost immediately, the comet began to defy expectations. As it continued its inbound journey through the early months of 2020, it started to brighten at a ferocious, almost unprecedented rate. Most comets follow a predictable curve, their brightness increasing steadily as they approach the Sunday. But Atlas was on a tear. Week by week, it surged in luminosity, far outstripping the most optimistic projections. By March, it had brightened over 4,000-fold since its discovery. Amateur astronomers who had initially needed large telescopes and sensitive cameras to catch a glimpse were now tracking it with relative ease. The scientific community was buzzing with excitement. The comet's orbit was remarkably similar to that of the Great Comet of 1844, leading to speculation that Atlas could be a fragment of a much larger parent body that had disintegrated centuries or even millennia ago. If so, its composition might be more volatile, more prone to spectacular outbursts, as previously unexposed pockets of ice were suddenly exposed to sunlight. Projections based on its incredible rate of brightening were almost dizzying in their promise. Extrapolating its light curve forward suggested that by the time it reached its closest approach to the Sun in late May, it could rival the planet Venus in the sky, a brilliant beacon easily visible to the naked eye even in twilight. Some whispered it could become the brightest comet in a generation, perhaps one of the greatest of the century. The world, just entering a period of unprecedented uncertainty and isolation, began to take notice. News headlines eagerly trumpeted the arrival of a potential once-in-a-lifetime celestial spectacle. A messenger from the dawn of time was hurtling towards us, promising to paint a magnificent streak of light across our spring skies. For scientists, it was a golden opportunity to study a pristine visitor from the Oort cloud, to analyze the raw ingredients of our solar system as they were vaporized by the Sunday. For the rest of us, it was something simpler, more elemental. A chance to connect with the cosmos, to witness a display of profound, silent beauty. The anticipation was palpable. All eyes, from professional observatories to backyard telescopes, were turning toward this single accelerating point of light. Comet Atlas was not just a scientific curiosity anymore. It had become a vessel for our collective hopes, a promise of light in a darkening world. It was on course to put on a show for the ages, a historic performance set to unfold in the grand theatre of the night sky. And as it raced toward its fiery destiny, no one could have possibly imagined the dramatic twist its story was about to take. And so, with the world's gaze fixed upon it, Comet Atlas sailed onward, a messianic beacon, promising a celestial revelation. In those early intoxicating months of 2020, every new image, every updated measurement, seemed to confirm the grand prophecy. Its light curve, that critical chart tracking its brilliance against time, was a line of pure, unadulterated ambition rocketing upwards on a trajectory that defied even the most optimistic models. We were witnessing the birth of a legend, a story we would one day tell our children of the time. A visitor from the dawn of the solar system returned to blaze across our skies. The narrative was set, the stage was lit, and humanity leaned in, ready for the overture. But in the silent, sterile rooms where data streams replaced starlight, a different story was beginning to be told. It wasn't a shout, not yet. It was a whisper, a subtle deviation from the beautifully orchestrated script we had all come to believe. At the world's great observatories, automated telescopes sipped photons from Atlas night after night, feeding their findings into algorithms programmed with the immutable laws of physics. And these algorithms, devoid of hope or expectation, began to flag an inconsistency. The magnificent crescendo, the comet's relentless climb towards glory, was beginning to falter. The upward slope of its light curve, once so steep and certain, was now showing signs of hesitation. It was leveling off a subtle flattening that a casual observer would never notice, but to a cometary scientist, it was a discordant note in a perfect symphony. Initially, it was dismissed as noise, an instrumental artifact, or perhaps a temporary phase in the comet's outgassing. Comets, after all, are notoriously fickle beasts, their icy hearts prone to unpredictable outbursts and quiescent periods. The thinking was that Atlas was simply taking a breath before its next great surge, as it plunged ever closer to the sun's searing forge. But the breath lingered. The pause became a plateau. The data pouring in from Hawaii, from Chile, from the Canary Islands all told the same unsettling tale. The celestial engine, which had roared with such astonishing power, was sputtering. It was still a remarkably bright object, far brighter than it had any right to be, but it was no longer following the path of its legendary predecessors, comets like Hale-Bopp or McNaught. It was charting a new, more worrying course. While this quiet drama unfolded in professional circles, the public narrative continued its jubilant march. Backyard astronomers, armed with increasingly powerful telescopes, were still capturing breathtaking images. The comet's vast ethereal coma of green gas had expanded to a mind-boggling scale, appearing larger than the planet Jupiter in the sky. Its tail, a delicate streamer of dust and ions, was beginning to unfurl, a cosmic windsock pointing away from the Sunday. The excitement was a palpable force, a global current of shared wonder in a world gripped by uncertainty. Forum posts exploded with new observations, families planned trips away from city lights, and the media fanned the flames of anticipation. The disconnect between the professional data and the public experience had become a chasm. One saw a dream beginning to dim, the other saw a spectacle still growing in grandeur. This strange paradox, this duality of perception couldn't last. The first cracks in the public-facing facade came not from complex graphs of photometric data, but from the keen eyes of the most dedicated amateur observers. These were not casual stargazers, but seasoned veterans who knew the sky's subtle language. They began to notice that while the comet's gaseous envelope was impressively large, its core, the brilliant pinpoint of light, known as the pseudo-nucleus, seemed off. It lacked the sharp, stellar concentration of a healthy, active comet. There was a softness to it, a diffuseness that hinted at a lack of integrity. Their reports, at first cautious, started to percolate through the community. The numbers weren't adding up. The visual magnitude, estimates and measure of brightness, were consistently coming in fainter than the official projections. A murmur of confusion began to ripple through the very communities that had been the comet's most vocal champions. Why was it so big yet so stubbornly faint at its heart? The answer would come not with a whimper, but with a series of catastrophic revelations. The professional observatories, now intensely focused on the comet's strange behavior, turned their most powerful instruments to its core. They were no longer just measuring its brightness, they were dissecting its very anatomy. What they found confirmed their worst fears and triggered the final tragic act of the comet's public life. High-resolution images, painstakingly processed to cut through the glare of the coma, revealed the unthinkable. The singular diamond point nucleus that had anchored this magnificent celestial apparition was no longer singular. It had elongated, stretched. The gravitational and thermal stresses of its journey, the very forces that were meant to ignite its final glorious display, were instead tearing it limb from limb. Imagine a mountain of ice and rock older than the Earth itself, held together by the deep cold of interstellar space for 4.5 billion years. Now imagine that mountain being dragged towards a celestial blowtorch. The gentle warmth that had first woken it from its slumber had become a relentless assault. Fissures born from thermal shock would have spiderwebbed across its surface. Jets of gas, once the source of its beauty, would have erupted with uncontrolled violence, acting like chaotic rocket thrusters spinning the nucleus faster and faster. The delicate gravitational balance that had preserved it for eons was broken. The great comet was beginning to fail. The elongation seen in the images was the first sign of this structural collapse, a prelude to total disintegration. The confirmation came from the most powerful eye we have, the Hubble Space Telescope. Its gaze, unhindered by Earth's turbulent atmosphere, was directed at the ailing comet. The images it returned were both heartbreaking and scientifically stunning. The once solid core had fractured into a cascade of smaller pieces. It was a cosmic shipwreck, a ghostly flotilla of icy debris sailing along the same orbital path, each piece a miniature comet in its own right, feebly trying to create its own coma and tail. The initial images showed 2, then 3, then 4 distinct fragments. Within days, astronomers were counting dozens. Atlas wasn't a comet anymore. It was a funeral procession, a string of dying embers where a brilliant bonfire had been promised. This was the smoking gun. The reason for the stalled brightening was now brutally clear. A comet's brilliance comes from sunlight reflecting off the dust and gas ejected from its nucleus. By breaking apart, Atlas had dramatically increased its surface area, causing a brief final surge in brightness as fresh ice was exposed to the sunday. But this was a death throw, not a sign of life. The smaller fragments, lacking the mass and gravitational cohesion of the parent body, were vaporizing at an alarming rate. They were sublimating into nothingness like snowflakes on a hot skillet. Instead of one large, efficient engine of cosmic dust, there was now a collection of small, sputtering and rapidly vanishing pieces. The source of the spectacle was destroying itself. The news rippled out from the astronomical community, and the tone of the global conversation shifted almost overnight. The jubilant headlines were replaced with somber scientific postmortems. The social media feeds filled not with wonder but with disappointment and a sense of shared loss. The comet of the century was now the great disappointment. For countless people it was a dream dissolved, a promise of natural wonder snatched away at the last moment. The celestial show was cancelled. The steady, inexorable plunge in brightness began. It was no longer a subtle flattening of a curve. It was a freefall. Each night, Atlas was visibly fainter than the last. The beautiful green coma, once so vast, began to thin out, becoming a transparent, ghostly shroud. The fledgling tail dissipated, its structure lost as the fragments dispersed. It was during this precipitous decline that the comet entered the domain that gives our story its name, the Blackout Zone. This isn't a physical place in space, but a threshold of perception. It is the point at which an object becomes too faint, too diffuse for the vast majority of public telescopes to resolve. It is the line that separates a shared communal spectacle from a specialized professional object of study. One by one, the backyard observers who had so eagerly charted its rise now reported its disappearance. Where once they saw a fuzzy patch of light, now there was only the familiar star-dusted blackness of the background sky. The comet hadn't vanished, not entirely. It had simply slipped beyond our reach, retreating from the realm of public wonder into a purgatory of scientific observation. For the world's largest telescopes, the hunt was still on. For them, the Blackout Zone was not an end, but a new beginning. The challenge was no longer to witness a spectacle, but to perform a cosmic autopsy. They could still track the largest, most resilient fragments of the shattered nucleus, watching them fade and disperse like smoke on the wind. Each photon captured was now a precious clue, a piece of a puzzle that had shifted from what will it become to what went wrong. The ghost of Atlas was still whispering its secrets, but only to those with the most sensitive ears, the most powerful eyes. For everyone else, for the millions who had looked up with such hope, there was only silence. The great visitor had come promised us the show of a lifetime, and then before our very eyes had vanished into the darkness, leaving only the faintest of memories and the deep resonant mystery of its own spectacular and ultimately tragic demise. The numbers arriving from observatories across the planet were no longer just contradictory. They were becoming nonsensical. What had begun as a gentle, predictable rise towards celestial stardom, a clean, elegant curve on a graph, had devolved into a chaotic fever chart. The light from Comet Atlas, that distant harbinger of a promised spectacle, was fluctuating wildly, erratically, almost violently. For every report of a sudden hopeful surge in brightness, another would follow, detailing an inexplicable dip, a fading that defied all the established models of cometary behavior. It was as if the comet, in its silent journey through the void, was fighting against itself. Astronomers who had staked their reputations on its glorious arrival now stared at their data streams with a growing sense of unease, a creeping suspicion that we weren't witnessing a coronation. We were watching a catastrophe unfold in agonizing slow motion 60 million miles away. The great hope of 2020 was beginning to look less like a rising star and more like a dying patient, its vital signs flickering across our screens in a language we were struggling to comprehend. The Blackout Zone was no longer just a region of space where Atlas would be hidden from us. It was becoming a metaphor for our own understanding. We were flying blind, chasing a ghost whose true nature remained maddeningly out of reach, a puzzle that grew more complex with every passing hour. On the ground, under the vast, unblinking eyes of our terrestrial telescopes, the first unsettling clues began to surface. These were not the crisp, revelatory images you might imagine. They were subtle, almost subliminal shifts in the data whispers from the edge of visibility. Professional and amateur astronomers alike, scrutinizing their nightly captures, started reporting a peculiar change in the very heart of the comet. The central condensation, the brilliant star-like point of light known as the nucleus, was losing its definition. Where there should have been a sharp, diamond-hard point, there was now a strange elongation, a soft, nebulous blur that seemed to stretch along the comet's direction of travel. It was a smudge where a pinprick should be. Initial reports were dismissed as atmospheric distortion, poor seeing conditions, or wishful thinking. Yet the reports kept coming, independent confirmations from different continents, all telling the same disconcerting story. The comet's core was fuzzy. It lacked the integrity, the solid center of mass that a healthy, cohesive nucleus should possess. Computer enhancement techniques pushing the limits of the collected light hinted at something even more profound. The single, blurry object seemed to resolve ever so faintly into multiple indistinct points of light huddled together within the glowing coma. It was like trying to discern the number of headlights on a distant car through a thick fog. You know something is there, but its form, its very wholeness, is an illusion. The evidence was tantalizingly incomplete, a cosmic crime scene with only the faintest of fingerprints. But for those who knew how to read the signs, a chilling hypothesis began to take shape. Comet Atlas wasn't just dimming, it might be disintegrating. It could be dissolving back into the primordial dust from which it came. The problem was, from down here, trapped beneath 100 kilometers of turbulent air, we could never be certain. To truly know, to pass judgment on the fate of this celestial traveler, we needed a witness with an uninterrupted view. We needed to call upon the greatest astronomical observatory ever built. We needed to turn the unblinking eye of Hubble toward the fading apparition. The decision was not made lightly. Pointing the Hubble Space Telescope is a matter of intense competition and meticulous planning. Its time is scheduled months, even years in advance, a precious resource allocated to cosmology's most profound questions. To interrupt that schedule for a target of opportunity, a so-called transient event requires extraordinary justification. A potentially fragmenting comet, one that promised to be the astronomical event of the decade, was just such a justification. The request was fast-tracked through the highest levels of astronomical authority, a digital siren call echoing from Earth to the orbiting observatory. High above the blurring effects of the atmosphere in the perfect silent clarity of low Earth orbit, Hubble began its slow, deliberate pivot. Its vast mirror, a marvel of polished glass 2.4 meters across, swung silently through the vacuum, locking onto coordinates that marked a specific lonely point in the constellation of Camelopardalis. This was not just another observation. It was an act of celestial forensics. Hubble was not being asked to merely look. It was being tasked to conduct an autopsy from a distance of 60 million miles. Its powerful optics, capable of resolving details with astonishing precision, would cut through the glowing shroud of the coma, bypassing the fog of gas and dust. It would stare directly into the heart of the mystery, into the very soul of Comet Atlas, and return a verdict. The command was sent. The light, having travelled for minutes across the inner solar system from the troubled comet, was collected, focused, and recorded. And as the first packets of data began their own journey back to Earth, a community of scientists held its collective breath, waiting for the truth to be revealed. The images that would appear on their screens would not just solve the riddle of the fluctuating light curve. They would forever change our relationship with this comet, transforming our great hope into a profound and beautiful tragedy. The ghost was about to give up its secrets. The data streamed down from orbit, reconstructed line by line into an image of stark, heartbreaking clarity. Where we had all expected to see a single brilliant nucleus, a solid, icy mountain hurtling through space, Hubble revealed something entirely different. There was nothing, no single point of light existed. In its place hung a ghostly, ethereal procession, a funeral train of shimmering fragments drifting silently through the void. It was a string of incandescent pearls where a single diamond should have been. The images, captured over 2 days, showed not 2 or 3 pieces but dozens. Some were the size of a house, others as large as a sports stadium, each a miniature comet in its own right, trailing its own faint tail of dust and gas. They were spread out over a distance of thousands of kilometers, a chain of gravitational shrapnel slowly, inexorably pulling apart from one another. This was the definitive proof, the smoking gun. Comet Atlas had not just cracked, it had suffered a catastrophic structural failure. It had shattered. The beautiful, glowing object that had captivated the world was in reality a celestial ghost, a luminous cloud of debris marking the gravestone of a once mighty nucleus. Watching the time-lapse sequences from Hubble was like witnessing the final silent moments of a dying creature. You could see the fragments separating their relative positions, shifting their individual comas of dust and gas puffing out into space like fading breaths. The brightest fragments, designated A and B by astronomers, were themselves unstable, showing signs of further fracturing even as Hubble watched. It was a cascade of self-destruction, a chain reaction of disintegration playing out on a cosmic scale. The mystery of the erratic light curve was instantly and dramatically solved. The comet's initial spectacular brightening had been a death gasp. As the nucleus first began to fracture, it exposed enormous new surface areas of fresh, volatile ice to the sunlight. This triggered a massive short-lived surge in outgassing, creating a huge reflective cloud of dust that made the comet appear deceptively brilliant. But it was an illusion, a final brilliant fever before the end. Once that initial burst of material dissipated, and with the core now shattered into smaller, less productive pieces, the light production plummeted. The heart of the engine had been ripped out, and all we were seeing was the fading glow from the wreckage. Hubble had not just given us an answer, it had made us witnesses to the very moment of the comet's demise. We were watching it dissolve before our very eyes. But what cosmic force could be powerful enough to annihilate an entire mountain of ice and rock? How could an object that had likely survived for 4.5 billion years, orbiting in the frozen dark of the Oort cloud, simply fall apart? On its first fiery pass through the inner solar system, the answer lies in a trio of relentless, destructive processes, a perfect storm of physics that turned the comet's own nature against it. The first assailant was the sun itself, not its gravity but its sheer, unadulterated heat. As Atlas drew nearer to our star, it was subjected to an immense thermal shock. Imagine taking a block of ice from a deep freezer and plunging it into boiling water. The outer layers expand rapidly, while the core remains frigid and contracted. This immense temperature gradient creates powerful internal stresses, propagating microscopic fractures deep within the object's structure. For a comet, a loose agglomeration of ice and dust held together by little more than its own feeble gravity, these thermal cracks can be devastating. The side of the nucleus facing the sun would bake, reaching temperatures well above freezing, while the side facing deep space remained locked at hundreds of degrees below zero. This constant, brutal cycle of heating and cooling day after day, week after week, acted like a celestial hammer and chisel, relentlessly working to weaken the comet's internal cohesion, prying it apart from the inside out. It was being cooked and frozen at the same time, a torturous process that prepared it for the final fatal blows. The comet was being tenderized for the kill, its structural integrity compromised before the real violence even began. The second force at play was the comet's own lifeblood, its jets of outgassing volatiles. We tend to imagine these as gentle, beautiful plumes, but the reality is far more violent. As sunlight heats the surface pockets of frozen gases like carbon monoxide, carbon dioxide, and water ice sublimate, bursting forth into the vacuum of space. These are not graceful fountains. They are powerful, explosive jets acting like miniature rocket engines all over the nucleus. A healthy, stable comet might have these jets firing in a balanced, symmetrical way, gently pushing the comet along its path. But Comet Atlas, being a primordial body, was likely not a uniform sphere. It was probably a lumpy, irregular object, a dirty snowball in the truest sense. On such an object, the jets would fire unevenly, erratically. A strong jet erupting from one side, with no corresponding jet on the other, would do more than just push the comet. It would begin to nudge it into a spin. Over time, as more and more of these asymmetrical thrusts occurred, the spin would accelerate. The comet effectively became a victim of its own activity, a celestial machine with its thrusters firing randomly, pushing it faster and faster into a dizzying rotation. This process, known as spin-up, is a notorious killer of comets. The gentle celestial wanderer was being transformed into an out-of-control spinning top, setting the stage for the third and final act of its destruction. The very process that made the comet beautiful to behold, the outgassing that created its magnificent coma and tail, was also the engine of its own undoing. It was a tragic built-in flaw, a self-destruct mechanism coded into its very essence. This brings us to the final decisive blow: rotational force. As the asymmetrical jets spun the nucleus faster and faster, a powerful centrifugal force began to build from its core outwards. It is the same force that presses you against the wall of a spinning carnival ride, the force that would tear a speeding flywheel to pieces if it spins too fast. A solid rocky body like an asteroid can withstand immense rotational stress, but a comet nucleus has virtually no tensile strength. It is a fragile conglomerate, a loose pile of ice dust and rock held together by chemical bonds, weakened by eons of cosmic ray bombardment and the recent intense thermal stresses. It possesses the structural integrity of a loosely packed snowball. As the spin rate of Atlas increased, this outward centrifugal force eventually grew to overwhelm the comet's own feeble gravity and fragile internal structure. The nucleus reached a critical tipping point. The forces trying to hold it together were simply no match for the forces trying to fling it apart. At that moment, the cracks that had been forming from thermal stress were violently ripped open. The entire structure failed at once. The spinning mountain of ice and rock, unable to bear the strain any longer, simply disintegrated. It flew apart, shattering into the dozens of pieces that Hubble so clearly saw. It wasn't an explosion in the traditional sense, but a quiet, inexorable surrender to physics. The celestial blowtorch of the sun had weakened it. The rocket-like jets of its own gases had spun it into a frenzy, and the resulting centrifugal force acted as the executioner, delivering the coup de grace. The great comet was dead, survived only by a ghostly fleet of its own fragments, each one a testament to the brutal, unforgiving mechanics of our solar system. The spectacle was over before it had even truly begun. The promise of a generational comet, a brilliant sword of light in our night sky, had been extinguished. The bright, condensed object that backyard astronomers had tracked with such excitement had been replaced by a diffuse, elongated smear, a faint and mournful glow that would itself soon fade into nothingness. Its light curve, once a beacon of hope, now served as its epitaph, a graphic story of its violent final days. But the death of Comet Atlas was not an ending. For science, it was a profound and unexpected beginning. We had been granted a ringside seat to one of the most fundamental and elusive processes in the solar system, the death of a comet. The wreckage, that ghostly funeral procession of fragments now drifting through the Blackout Zone, carried with it the answers to deeper questions. Each piece was a time capsule, a pristine sample of the material from which our Earth and the other planets were formed 4.5 billion years ago. The comet's disintegration, while a loss for stargazers, was an extraordinary gift to science. The ghost ship, though broken, was now on a new heading, its cargo of ancient secrets spilling out into the open. And as its scattered remains continued their silent journey toward the sun, they would tell us a different story, not of a great spectacle that might have been, but of the raw, primordial ingredients that gave birth to us all. The king was dead, but its legacy was only just beginning to be understood. And so the promise of a lifetime, the great celestial spectacle we had all been waiting for, simply vanished. It did not fade with dignity, nor did it exit the stage with a final brilliant bow. Instead, Comet Atlas shattered its cohesive whole, dissolving into a ghostly retinue of fragments, a trail of cosmic breadcrumbs scattered across the interplanetary dark. For the millions who had tracked its progress with backyard telescopes and binoculars, the show was abruptly, cruelly over. The single, hopeful point of light they had followed night after night was gone, swallowed by the immense blackness it was meant to conquer. The Blackout Zone was no longer a future region of the sky where the comet would be hidden by the sun's glare. It became an immediate reality, a curtain that had fallen prematurely. The comet had in effect created its own blackout, not by moving behind an obstacle, but by ceasing to exist as a singular discernible object. What you must understand is that the light from Atlas never truly disappeared. The laws of physics are unforgiving on this point. The total amount of sunlight reflecting off the cometary material remained for a time roughly the same. The problem was one of concentration. Imagine a single brilliant mirror catching the sun and focusing its glare into a dazzling beam you can see from miles away. Now imagine shattering that mirror into a million microscopic pieces and casting them into the wind. The same amount of glass is there, the same amount of sunlight is hitting it, but the focused, coherent beam is gone. All that remains is a faint, almost imperceptible shimmer, a haze of light too diffuse and too tenuous for the human eye, or even a modest telescope to resolve against the infinite backdrop of space. This was the fate of Atlas. Its light, once a focused beacon of discovery, was now an ethereal fog of disappointment, its brightness diluted across a vast and expanding volume of space, each individual fragment a tiny fading ember where a great fire had once raged. For the public, this was the end of the story. But for the scientific community, an entirely new and in some ways more profound chapter was just beginning. The moment Atlas fractured it transformed from a passive object of observation into an active laboratory for celestial mechanics. The disappointment that rippled through the amateur astronomy community was met with a surge of adrenaline in professional observatories around the world. Every large telescope that could be trained on that patch of sky was immediately repurposed. The mission was no longer about witnessing a beautiful flyby. It was now a cosmic forensic investigation, a post-mortem on a scale that defies earthly comprehension. The death of the comet was infinitely more revealing than its life might ever have been. A healthy, intact comet guards its secrets, jealously shrouding its nucleus in a thick, obscuring coma of gas and dust. We can only infer what lies beneath studying the chemical composition of its exhalations. But a shattered comet has been violently dissected for us. Its primordial heart lay bare for our instruments to analyze. The great telescopes of Earth instruments like Hubble Keck and the Very Large Telescope became our remote probes, our interplanetary coroners. Their immense light-gathering power, far exceeding anything available to the public, could still detect the feeble glimmers of the largest fragments. While your backyard telescope saw only blackness, these titans of astronomy saw a dynamic, evolving crime scene. They could resolve not just one or two pieces, but dozens, tracking their individual trajectories, measuring their brightness fluctuations, and most critically performing spectroscopy on the light they reflected. By splitting that faint ancient light into its constituent colors, its chemical barcode, astronomers could read the story written in the heart of Atlas. They were now analyzing material that had been locked away deep inside the nucleus since the very birth of the solar system 4.5 billion years ago. This was material that had never been processed by the sun's heat, never been altered by solar radiation. It was a pristine sample of the protoplanetary disk, the raw stuff from which Earth and all the other planets were forged. The comet's catastrophic failure had become humanity's extraordinary opportunity, turning the Blackout Zone into a treasure trove of invaluable data. The central question, the driving mystery behind this frantic worldwide observational campaign, was simple yet profound. Why? What cosmic force, what celestial assassin, had been responsible for this spectacular act of destruction? Comets are notoriously fragile objects, often described as dirty snowballs or icy dust bunnies. They are not solid monolithic rocks like asteroids. They are loose agglomerations of ice, dust, and rock held together by their own feeble gravity and frozen primordial gases. They are cosmic relics, survivors of a violent youth, but they are fragile survivors. As Atlas made its inexorable plunge toward the sun, it was entering the most hostile environment in the solar system. The forces arrayed against it were monumental, and the investigation into its demise focused on several key suspects, each a powerful agent of cosmic change. The first and perhaps most obvious culprit was the Sun itself, but not just through its heat. The primary suspect was gravity. As the comet approached the inner solar system, the Sun's gravitational pull intensified dramatically. This pull, however, was not uniform across the comet's body. The side of the nucleus facing the Sun was pulled more strongly than the side facing away, creating a differential force, a cosmic stretching known as a tidal force. It's the same force that causes Earth's oceans to bulge, creating our tides, but ramped up to an almost unimaginable degree. For a weakly bound object like Atlas, these tidal forces could have acted like a gravitational rack, relentlessly stretching and straining the comet's internal structure. Every kilometer it drew closer to the Sun, the tension mounted. Cracks that may have existed for millennia could have begun to propagate. Fissures deep within its icy heart could have widened until the strain became too much to bear. At a critical point, the Sun's tidal pull would have overwhelmed the comet's own gravity, the very force holding it together. The result would be a quiet, inexorable, yet utterly complete disintegration, as the comet was gently but irresistibly pulled apart. But there was another, more violent possibility, one driven by the Sun's other great weapon, its ferocious heat. For billions of years, Atlas had drifted through the frozen abyss of the Oort cloud, its temperature hovering just a few degrees above absolute zero. As it fell inward, it was subjected to a thermal shock of epic proportions. The Sun became a celestial blowtorch, its radiation flash-heating the comet's surface. This rapid, uneven heating could have created immense thermal stresses within the nucleus. Imagine pouring boiling water onto a frozen pane of glass. The sudden expansion of the outer layers, while the core remains frigidly cold, causes it to shatter. On a cosmic scale, the same principle applies. The surface of Atlas could have expanded and cracked, sending fractures deep into its frozen interior, catastrophically weakening its entire structure from the outside in. This process would be accelerated by the very nature of comets. As the ices on the surface were heated, they didn't melt. They sublimated, turning directly from a solid into a gas. This sublimation process points to a third suspect, a kind of self-destruction. The jets of gas erupting from the warming nucleus, the very phenomena that create a comet's beautiful tail, could have also been the architects of its doom. If the nucleus was not a perfect uniform sphere, which it certainly was not, then these jets would not fire evenly. Pockets of highly volatile ices like carbon monoxide or frozen nitrogen buried just beneath the surface would act like explosive charges waiting to be detonated by the Sun's warmth. When they finally erupted, they would do so with tremendous force, not only spewing dust and gas into space, but also imparting a torque on the nucleus itself. This could have spun the comet up faster and faster like a child's top. We have seen this with other comets. The Yorp effect, a subtle push from sunlight itself, can gradually alter an object's rotation over eons. A sudden powerful jet, however, can do the same thing in a matter of days or hours. As the rotational speed increased, centrifugal forces would build, pulling the comet apart from the inside out. It would be a battle between the inward pull of its own gravity and the outward fling of its rotation. For a fragile rubble pile like Atlas, it was a battle it was destined to lose. At a certain spin rate, it would simply fly apart its own motion, becoming the agent of its execution. Astronomers studying the debris field were looking for clues to distinguish between these scenarios. If tidal forces were the primary cause, the fragments would be expected to drift apart relatively slowly, moving along very similar orbital paths in a long-ordered chain. It would be a relatively clean, almost gentle separation. If, however, the breakup was caused by a violent outgassing event or an internal explosion, the debris field would look very different. The fragments would be pushed away from each other with much higher velocities and in more random directions. The spray of shrapnel would be more chaotic, a testament to a more energetic, explosive event. The initial data from Hubble seemed to suggest a more complex story. The main fragments were indeed drifting apart slowly, forming a loosely organized string of pearls, a signature consistent with a tidal disruption or a gentle rotational breakup. Yet there were also fainter, faster-moving clouds of dust, hints of more explosive processes at play. This pointed toward the most likely scenario of all, not a single cause of death, but a conspiracy of cosmic forces working in concert. It's entirely possible that Atlas was a fundamentally flawed structure from its very creation. Perhaps it was two or more smaller cometesimals that gently collided billions of years ago, sticking together but never truly fusing into a single strong body. It would have a weak seam, a structural fault line running through its core. As it approached the Sun, all the suspects would have gone to work on this pre-existing weakness. The Sun's tidal forces would have begun to gently pry at that seam. The thermal shock would have sent fractures racing towards it. Then, a few well-placed jets, firing as volatile ices were exposed along the fault line, could have provided the final fatal push, torquing the nucleus until it snapped along that ancient fragile boundary. It wasn't one murderer, but a gang, each contributing to the inevitable outcome. The comet wasn't just killed, it was systematically dismantled by the physics of the inner solar system. Each fragment told a piece of this story. By tracking the exact motion of each chunk of debris, astronomers could run the clock backwards, simulating their trajectories back to the moment of separation. This allowed them to pinpoint not only when the breakup occurred, but also times in the nucleus each piece originated. They could build a three-dimensional map of the comet's ghost, reconstructing its internal structure from its shattered remains. The brightness of each piece also fluctuated, tumbling end over end in the sunlight. These flickers of light were not random, they were data. By analyzing the light curves, the precise patterns of brightening and dimming, scientists could deduce the shape of each fragment and how fast it was rotating. This revealed that the breakup itself had sent the pieces spinning, a clear sign that powerful torquing forces were involved. The Blackout Zone, once a symbol of what was lost, had been transformed by science into a unique celestial laboratory, an autopsy table millions of kilometers long. We were sifting through the wreckage not to mourn what could have been, but to understand the fundamental nature of these primordial visitors. The demise of Atlas served as a stark and beautiful reminder of the ephemeral nature of these cosmic wanderers. We see them as timeless ancient objects, but their journey through our neighborhood is a trial by fire. Many, perhaps most, do not survive it. They are torn apart, they evaporate, they fizzle out. For every brilliant Hale-Bopp or majestic McNaught that graces our skies, there are countless others like Atlas that promise greatness only to crumble under the immense pressure of their solar encounter. This is not failure, it is the natural violent life cycle of a comet. And the data harvested from Atlas's spectacular death has provided us with an unprecedented look into that cycle. It has helped us refine our models of cometary structure, forcing us to see them not as simple snowballs, but as complex heterogeneous bodies with varied compositions and deep-seated structural flaws. This knowledge is not merely academic. It is vital for understanding the delivery of water and organic molecules to the early Earth, and crucial for assessing the potential threat posed by any future comet that might venture too close. The fragments, now a diffuse and ever-expanding cloud, continue their silent journey. They are too faint to be seen by all but the most powerful instruments, a ghostly funeral procession rounding the sun where a king was meant to pass. Each piece carries with it a part of the original comet's legacy, a fragment of its history now following its own distinct path into the future. They are a monument to a cosmic promise unfulfilled, yet also a testament to our own relentless curiosity. We looked into the darkness where a brilliant light had been, and instead of an empty void, we found a wealth of answers. We found a story of violence and fragility, a story of heat and gravity, a story written in the language of physics across a canvas of interplanetary space. The great comet was dead, but in its place a new and more intricate understanding was being born. The journey through the Blackout Zone was far from over. It had merely changed its nature from a voyage of anticipation to one of profound and unexpected discovery. And so the great silence began. The celestial messenger, which had promised to scribe an unforgettable chapter in our skies, had vanished. For millions of you peering through backyard telescopes into the deepening twilight, the stage was simply empty. The Blackout Zone was no longer just an astronomical term. It was a felt experience, a profound and sudden void where a beacon of cosmic history should have been. The anticipation that had electrified the global community collapsed into a shared, quiet disappointment. The comet was gone. Our connection to this ancient traveller, it seemed, had been severed. But for a dedicated few, the investigation had just begun. Here, in the hollow echo of the comet's passage, the real work was starting. For these astronomers, the disappearance was not an ending, but the universe posing its most tantalizing kind of question, a mystery written in invisible ink. The challenge was immense, a riddle wrapped in the vacuum of space. How do you study something that is no longer there? How do you perform an autopsy on a ghost? The answer, it turns out, was not to look for the comet itself, but for the faint, lingering spectres it had left behind. The crime scene, though unimaginably vast and utterly dark, was not entirely clean. The first clues came not as images, but as whispers of light captured by the largest and most sensitive eyes on our planet. While your telescope could no longer find a distinct point of light, observatories like the Hubble Space Telescope could still detect something else. An ethereal wraith-like haze, a barely perceptible stain against the blackness where Atlas was supposed to be. This was the ghost of the coma, the comet's once majestic atmosphere, now a tattered, dissipating shroud. To the naked eye it was nothing, but to the specialized instruments of modern astronomy this tenuous cloud was a treasure trove of information, a final message from the heart of the dying wanderer. They turned to one of science's most powerful forensic tools, spectroscopy. You can think of it as a cosmic prism. Just as a prism splits sunlight into a rainbow, a spectrograph takes the faint blended light from a celestial object and dissects it, spreading it out into its constituent wavelengths. And inscribed within this spectrum like a chemical barcode are dark or bright lines that betray the precise elements and molecules present in the light's source. For generations we have used this technique to know what distant stars are made of, to understand the atmospheres of alien worlds. Now it was being deployed to read the last will and testament of a disintegrated comet. The light they gathered was painfully faint, a mere trickle of photons that had journeyed millions of kilometers only to be caught and dissected. The initial spectra were haunting. They confirmed the presence of the usual cometary suspects, the molecules that are cooked off an icy nucleus as it nears the sun's fire. Cyanogen, a simple molecule of carbon and nitrogen, was there, glowing with a faint characteristic signature. So was diatomic carbon, 2 carbon atoms, bonded together a substance so reactive it can only exist in the near-perfect vacuum of space. These were the expected fingerprints, the proof that what they were seeing were indeed the last vestiges of Comet Atlas. But the true story was not in times what times was there, but in how it was behaving. As the days and weeks went on, the team kept taking these spectral snapshots, building a timeline of the comet's final moments. A healthy, active comet should behave predictably. As it gets closer to the sun, the heat increases, more ice turns to gas, and the production of molecules like cyanogen should rise in a smooth, steady curve. Atlas, however, was telling a very different and far more violent story. Its molecular output was erratic, sputtering. The spectral lines would surge and then fade, not with the gentle rhythm of a sublimating ice ball, but with the chaotic cadence of a dying engine. It was as if they were listening to the comet's heartbeat and finding a catastrophic arrhythmia. One day, a surge in cyanogen suggested a large, fresh surface of ice had been suddenly exposed to sunlight. A few days later, the signal would plummet, indicating that the source had been exhausted or had broken away. This was not the graceful swan song of a comet fading into the night. This was the sound of something breaking apart. The spectral data was painting a grim picture of a body in the midst of a violent structural collapse. The nucleus wasn't just shedding gas and dust. It was fracturing, splintering into pieces, each piece a miniature short-lived comet in its own right, flaring up briefly before its own small reservoir of ice was depleted. The ghost in the machine was screaming, telling a story of disintegration. This revelation solved one part of the puzzle. Atlas didn't simply fizzle out. It suffered a cataclysmic structural failure, but this only opened up a deeper, more profound mystery. If it broke apart, where did the pieces go? Why couldn't we see them? Even a smaller fragment should still catch the sunlight, still shine as a tiny point in the darkness. Yet the blackout zone remained stubbornly, impenetrably black. The astronomers had found the cause of death, but the body, or rather the bodies, were still missing. To find them, they would need to move beyond the study of light and into the realm of pure gravitational mathematics. They had to stop looking for what they could see and start calculating where the unseen times must times be. This is where the investigation took a turn toward the truly extraordinary, becoming a feat of celestial mechanics that bordered on prescience. The team had a starting point, the last known precise orbit of Comet Atlas, before it vanished. They knew its trajectory, its velocity, its exact path through the solar system. From that single elegant arc, they could begin to build a new kind of model. They were no longer tracking one object, but a phantom cloud of possibilities. They had to treat the original comet as a kind of gravitational parent, and then predict the behavior of its unseen children. Imagine throwing a fragile glass ornament into the air. For a moment it flies in a perfect, predictable parabola, but then, at the peak of its arc, it shatters. The individual shards will fly off in slightly different directions, but their collective motion, their center of mass, will continue to follow that original perfect parabola. The astronomers tracking Atlas were faced with this exact problem, only on a cosmic scale. The comet had shattered, and the resulting fragments, though now invisible, were not free from the laws of physics. They were still tethered by the sun's gravity, their paths forever dictated by the momentum of their parent. They were gravitational breadcrumbs scattered along the original trail. The task fell to powerful supercomputers, which began running thousands upon thousands of simulations. Each simulation was a slightly different hypothesis for the comet's demise. What if it broke into 2 large pieces? What if it broke into 10, or 100, or 1,000 tiny ones? What if the fragmentation was a single explosive event? Or what if it was a slow, grinding process over several days, as the spectral data seemed to suggest each of these scenarios would produce a unique debris field, a cloud of fragments with a subtly different shape, size, and velocity distribution? The computer models churned through the physics, calculating the precise orbit for every single hypothetical fragment. They factored in not just the sun's immense gravity, but also the more delicate forces at play. They modeled the effects of outgassing the tiny jets of sublimating ice that could act like miniature rocket thrusters, gently nudging a fragment off its expected course. More importantly, they modeled the effect of solar radiation pressure. This is an incredibly subtle but persistent force, the gentle push exerted by sunlight itself. For a large object, this pressure is negligible. But for the very fine dust particles and small icy pebbles that would constitute a shattered comet, this constant stream of photons acts like a celestial wind, slowly and inexorably blowing the smallest debris away from the sun, separating the fragments by size. What emerged from these colossal computations was not a single answer, but a probability cloud, a ghostly 3-dimensional map showing where the fragments of Atlas were most likely to be. It was an astonishing piece of theoretical work, a portrait of an invisible debris field rendered in pure mathematics. And now came the moment of truth. They had to compare their elegant models to the messy reality of observation. They went back to the deepest images ever taken of that empty patch of sky images from Hubble and the great terrestrial observatories. They were looking for something that no human could ever spot by eye, a faint elongated smudge of light, a glow so diffuse it was almost indistinguishable from the background noise of the universe. And they found it. Buried in the digital data, precisely where the models predicted the densest cloud of fragments should be, was an incredibly faint, smeared-out signature. It was the combined, blended light of thousands of invisible pieces, none bright enough to be seen individually, but collectively producing a barely detectable sheen. The models that best fit this observation were the ones that simulated a catastrophic disintegration into a cascade of small, rapidly sublimating chunks. The pieces were too small to hold onto their ice for long. They flared up and then vanished within hours or days, becoming nothing more than dark, inert gravel. They were disappearing faster than the astronomers could even hope to track them individually. The verdict was in. The scientific mystery of the Blackout Zone was solved. Comet Atlas had been sentenced to death by the sun itself. It was a victim of thermal stress. As it drew closer to our star, the immense and unrelenting heat penetrated its dark, porous surface. The ancient, volatile ices trapped deep within its core ices that had been frozen in absolute darkness for 4.5 billion years began to boil, but they were trapped beneath a crust of rock and dust. The pressure built relentlessly, turning the comet's own heart into a geological time bomb. Finally, the strain became too much for its fragile, loosely packed structure to bear. It did not melt. It detonated from the inside out. The spectacle we had hoped for in the night sky was replaced by a far more profound and intricate one. Played out on computer screens, and in the lines of spectral data. The blackout zone, initially a symbol of our frustrated gaze, had been transformed. It was no longer a void, but a laboratory, a unique, unprecedented opportunity to watch a comet die in real time and to test the very limits of our ability to see the unseen. By studying its absence, by chasing its gravitational echoes and reading its final ghostly transmissions of light, we learn more about the life cycle of these celestial nomads than 1,000 brilliant passages might have ever taught us. We had witnessed the awesome, indifferent power of the cosmos to both create and destroy, and in the process we had honed the tools we would need to understand it. The story of Atlas was not one of failure, but of a new kind of discovery, one that required us to listen to the silence and find meaning in the dark. And so the great celestial performance ended not with a crescendo, but with a profound and lingering silence. The cosmic stage where Comet 3I Atlas was meant to blaze in a once-in-a-generation spectacle was left conspicuously empty. All the anticipation, the frantic calculations, the hopes of millions gazing upward, dissolved into the quiet darkness between the stars. The blackout zone, that simple geometric shadow cast by our proximity to the sun, fulfilled its promise. It swallowed the ghost of Atlas, leaving us on the other side, waiting for a phantom that would never emerge. For a moment it felt like a profound failure, a cosmic promise broken. We had gathered for a coronation and were left to witness a funeral conducted in absentia, a quiet and lonely disintegration far from our prying eyes. Yet it is here, in this perceived emptiness, in the very heart of this anticlimax, that the true, deeper story begins. The disappearance of Atlas was not an ending. It was a revelation, a different kind of discovery delivered not in a flash of light, but in the enduring power of its absence. We learned more from its death than we might ever have learned from its life. The first and most crucial lesson was etched into the very manner of its demise. This was no singular violent explosion, no celestial firework detonating in the void. Instead, what telescopes like Hubble witnessed in the final days was something far more subtle, more delicate, and infinitely more informative. Atlas didn't shatter, it crumbled, it unwound. It seemed to simply let go, surrendering its form back to the cosmos from which it came. This gentle, progressive fragmentation was a stunning real-world confirmation of a theory that had long been debated in the halls of planetary science, that many comets are not solid monolithic bodies of ice and rock. They are not cosmic cannonballs. Instead, they are fragile conglomerates, rubble piles held together by little more than ancient frozen gases and the faintest whispers of their own gravity. Imagine a handful of gravel and dust loosely packed with dry ice. That was Atlas, a celestial aggregate, a cosmic dust bunny born in the deep freeze of the outer solar system billions of years ago. It was a time capsule, but a fragile one, its structural integrity a secret it held close until its final journey. As it raced toward the sun, the gentle warmth of our star became a relentless, inescapable blowtorch. The process was insidious. It wasn't the heat itself that broke it apart, but the effect of that heat on the volatile ices trapped within its porous structure. These ancient frosts, which had been dormant for eons, began to sublimate, turning directly from solid to gas. Jets of vapor erupted from its surface, not as random plumes, but as powerful engines acting upon a weak and unstable airframe. These outgassing forces began to spin the nucleus faster and faster, creating a centrifugal force that the comet's feeble internal cohesion could not withstand. We were witnessing a gravitational gyroscope tearing itself apart from the inside out. The very thing that gave a comet its beautiful coma and tail its escaping gas and dust was also the mechanism of its own undoing. Each fragment that carved off the main body exposed fresh ice to the sunlight, accelerating the process in a runaway feedback loop of disintegration. The ghost of Atlas taught us that the life and death of a comet are inextricably linked, two sides of the same beautiful self-destructive process. Its ethereal glow was in truth the light of its own slow-motion dissolution. This was a cosmic post-mortem conducted from 100 million miles away, and the verdict was clear: the comet was simply too fragile, too loosely bound to survive the fury of its own awakening. This leads us to the second, more humbling lesson, a profound reminder of nature's inherent unpredictability. For all our sophisticated models and powerful computers, the universe always reserves the right to surprise us. We had plotted the orbit of Atlas with exquisite precision. We had equations to predict its brightness, its trajectory, its closest approach to the Earth and the Sunday. We had every reason to believe our forecasts were sound. But all of these calculations were based on one critical and ultimately false assumption that the comet was a single stable object that would behave as a single stable object should. We had accounted for the laws of gravity and thermodynamics, but we could not account for the comet's secret internal weakness. It was a catastrophic structural failure on a cosmic scale, the celestial equivalent of a bridge collapsing under a load it was never designed to bear. Atlas became a stark illustration of chaos theory playing out in the heavens, a testament to the fact that in complex systems, tiny, unknowable initial conditions can lead to dramatically different outcomes. An invisible fracture, a pocket of unusually volatile ice, a slightly less dense region within the nucleus, any one of these could have been the trigger for its ultimate collapse. This event forced a paradigm shift in how we approach cometary science. It proved that predicting a comet's brightness is not merely an exercise in orbital mechanics. It is a profound challenge in materials science and geology conducted remotely on an object we can barely see. We are not just tracking a point of light. We are trying to assess the structural integrity of a body we have never visited, whose internal composition is a complete mystery. The failure of Atlas to become the comet of the century was in fact a triumph for scientific humility. It exposed the boundaries of our knowledge, and in doing so showed us exactly where we need to explore next. It reminded us that our models are only as good as our assumptions, and that the cosmos is under no obligation to conform to our expectations. We must learn to embrace this uncertainty, to see it not as a failing of our science, but as the very frontier of our curiosity. The universe is not a perfectly oiled machine running on predictable clockwork. It is a wild, untamed, and gloriously chaotic place, and Atlas was our fierce and fleeting guide to that deeper truth. But the story of Atlas does not end in its dissolution nor in the humbling of our predictions. Its third, and perhaps most inspiring lesson, is a testament to the remarkable resilience and ingenuity of the scientific process itself. When the main event was so unceremoniously cancelled, astronomers around the world did not simply pack up their telescopes and go home. They pivoted. The collapse of the comet was not the end of the observation campaign. It was the beginning of an entirely new one. The target was no longer a single bright nucleus, but a ghostly trail of debris, a phantom string of pearls drifting through the void. This, it turned out, was an even richer scientific prize. When the comet was whole, its interior was hidden from us, locked away beneath a crust of dark, irradiated dust. Its fragmentation was like a cosmic excavation, a gift from the heavens. The sun had done for us what no spacecraft could have it, had peeled back the outer layers and exposed the comet's pristine primordial heart for our instruments to study. Observatories like the Hubble Space Telescope were retasked with unprecedented speed. Instead of one target, they now had dozens. They began to track the individual fragments, measuring their size, their rotation, their rate of sublimation. Each piece became a miniature comet in its own right, a natural laboratory for studying the physics of disintegration. By observing how these smaller chunks continued to fall apart and fade, scientists could build a much more detailed picture of the original body's composition. They could see differences between the fragments, suggesting the parent nucleus was not a homogeneous mixture but a complex body with distinct geological regions. It was like studying the individual bricks of a demolished building to understand how the entire structure was once put together. The light from these fading embers carried information about the types of ice and dust that had been frozen since the birth of the solar system. In its death, Atlas gave us the ultimate insider's view, a glimpse into the raw building blocks of planets that we could have obtained in no other way. This is the true power of science, not just to predict the future, but to extract profound knowledge from the unexpected, to find opportunity in failure, and to turn a spectacle's absence into a discovery's presence. And this brings us back to the Blackout Zone itself. Before, it was merely a frustration, a geometric quirk of our orbit that created a blind spot in the sky. It was a curtain falling at the most dramatic moment, obscuring the finale. But now we can see it differently. It is no longer just an empty space. It has become a destination. It is the graveyard of Atlas, the silent sun-scorched expanse where the final invisible act of its dissolution played out. The Blackout Zone is a reminder that the most important events in the universe often happen far from our view, and that absence itself can be a powerful scientific data point. The fact that nothing emerged from the other side tells us that the disintegration was total and complete. The silence from that region of space is not an absence of information. It is the information. It is the final, definitive statement on the comet's ultimate fragility. It has transformed from a simple zone of avoidance for telescopes into a symbol of cosmic finality, a place where the ephemeral nature of these celestial visitors is made starkly, powerfully real. It is the place where a river of primordial ice and dust finally met the solar fire and returned to the silence of interstellar space from which it was born. Looking ahead, the legacy of Atlas is not one of disappointment, but of preparation. The hard-won lessons from its ghostly passage are already shaping the future of planetary exploration. Missions like the European Space Agency's Comet Interceptor are being designed with the memory of Atlas firmly in mind. This ambitious mission will not target a known well-behaved comet. Instead, it will wait patiently in space for the discovery of a brand new pristine object hurtling in from the Oort cloud, an object that has never before approached a star. These are the most volatile, the most unpredictable, and potentially the most fragile comets of all perfect analogues of Atlas. The knowledge that such a body could easily disintegrate before the spacecraft even arrives fundamentally alters the mission's strategy. It will require a more cautious, more adaptive approach. The mission's 3 spacecraft design with a scout sent ahead to assess the target's stability is a direct response to the kind of catastrophic failure we saw with Atlas. We now know we must be prepared for our target to be not a solid object but a loose swarm of fragments, or perhaps nothing at all. Scientists are now building new models of cometary behavior that incorporate parameters for tensile strength and rotational forces, attempting to forecast not just a comet's path but its very survivability. Ground-based observation campaigns will prioritize looking for the early signs of splitting and fragmentation using the fate of Atlas as a template. The goal is no longer just to witness a spectacle, but to understand the underlying processes that govern these ethereal visitors. We are moving from passive observation to active diagnostic science, treating every new comet as a potential lesson in cosmic geology waiting to be unlocked. In a very real sense, the ghost of Comet Atlas will fly alongside every future mission, a constant reminder of the beautiful, untamable fragility of the objects we seek to understand. It has become a foundational cautionary tale, one that has made us wiser, more prepared, and ultimately better explorers. So we are left here under a sky that looks unchanged, yet our understanding of it has been forever deepened. We never saw the great comet we were promised. We were denied that brilliant streak of light against the tapestry of the stars. Instead, we were given something far more valuable, a profound and intimate lesson in the nature of creation and dissolution. We learned that some of the most beautiful things in the cosmos are also the most fleeting, held together by the barest of threads. We were reminded that our place as observers is one of humility, and that our greatest moments of insight often arrive disguised as disappointments. The story of Comet 3I, Atlas, is not about the light that failed to appear. It is about the understanding that blossomed in its place. It teaches us to look at the empty spaces with as much curiosity as we do the bright ones, to listen for the wisdom in the silence. For sometimes, the universe speaks most clearly not through the fire of a newborn star or the blaze of a majestic comet, but through the quiet, lingering echo of something magnificent that has vanished from sight, leaving behind nothing but the priceless gift of new knowledge.